Recording to this computer. I hope you guys are having a good start to your day. I hope that you had a good weekend. I hope that you have a good week ahead of you. If you got any exams, I know that my exam happened. I know Dr. Nassar's exam happened a couple days ago. So I presume that you got other classes where you have exams. And I wish for the best for you. One announcement that I got is up until today, I'm sorry you could not see the results of your exam. You could see like the score, like the one that I shared, but you couldn't actually see the right and wrong answers to every question. I fixed that this afternoon thanks to one of your classmates who joined me during office hours. I apologize. In the event that, that happens again, um, and I say, yeah, I did it. Uh, don't hesitate to say, I know that you think you did it, but you didn't. I won't take offense to that. Instead, I'll just be like, oh, I'll get mad at myself. Um, so I apologize for that. That's squared. One announcement that I've got is I've got that quiz B1. I pushed that one because it had some questions about isoelectric focusing. And that one was due before the last exam, but I went ahead and I pushed it. And so now it is due this Sunday. What I'm going to do is make this a extra credit quiz. So that's going to be like content that you look at on your own time. Um, I have to do some stuff with the grade book, move that to a location where it isn't counted, and then I have to add something back. Um, that will be hopefully kind of behind the scenes, so you won't see anything that like, oh my gosh, this brought my grade down or anything like that. What I'm gonna do though is I'm gonna go ahead and let everyone complete this quiz. I think right now there's 2 attempts. I'm gonna bump this one to 3 attempts in light of this new information. Um, Everyone's gonna have 3 attempts at this one. Um, And, after the grades have all been kind of added, that's whenever I'll go back and do the smoke and mirrors. Well, no, that's kind of a deception. So not smoke and mirrors. That's when I'll do the modification to make it actually appear as an extra credit grade. Um, so for a little throughout this week, it will be counted as however many points out of 10, but then end of the week, I'll make that adjustment. So expect grade adjustment. I'll say grade fix after 11 p.m. Sunday. Okay, so that's kind of my lone announcement for this lecture. Um, what I want to do is I want to go ahead and get cracking because we got a good bit of stuff. The next, I think I've got today's, Wednesdays, and Mondays lectures are all up. So you're welcome to look at those. I've kind of made some changes. For instance, I added the learning objectives. Here's what I want you to get out of this. Here's what I think is valuable information. And some of them are like, oh, yeah, be able to identify this structure. That seems pretty discrete and acute. But then other learning objectives are always the ones that are like, it's almost like you're pulling a thread on a sweater. So I've got these next 3 PowerPoints set up. Next Wednesdays, I'm gonna have up before the end of this week. Um, and then you'll be able to take a look at those. So here's our learning objectives for today. Today does have a good number of slides, but I've tried to make transitions from slide to slide a little bit more deliberate. And so although we have 47 slides in the PowerPoint, some of those slides might be like, oh, now, well, here is one. Boom. That's a whole slide. All that it did was grayed out the text and then highlighted this one. Because this is the first thing that we're going to get after, and this is knowing the proper use of various sugar terms. So kind of like jargon and terminology. So sugar is a targeted term and refers to simple molecules, monosaccharides and disaccharides, typically. So those terms saccharides, whether they're monosaccharides and disaccharides, Those are a little bit more general and refer to simple molecules as well as some polymers of these simple sugars. One example of a polymer is a disaccharide. Carbohydrates, so sugar, disaccharide, monosaccharide, and carbohydrates are all terms that I'm going to kind of use somewhat interchangeably. The ones that I want you to be most comfortable with in terms of, well, what does this mean? Would be the ones that include saccharide. So polysaccharide, monosaccharide, disaccharide. I mean, I could say trisaccharide, but that's not really a very important biological term. Um, so I always try to think about sugars as polymers and think about the base units, and the base unit being a monosaccharide. Um, so those are kind of the terms that we need to be comfortable with. Now, to tackle that first term, monosaccharides. Yes, absolutely. Tri and anything beyond that would kind of be an oligosaccharide. I think when it comes to an oligosaccharide, I think that the definition's like 3 to 15 or something like that. Um, but I would argue that more times than not, when you're talking about sugars, oh, okay, thank you. Um, when you're talking about sugars, the ones that are most biologically relevant to the ones that are most important are your, oh, great, thank you. Are you monosaccharides, disaccharides, and polysaccharides? Because those are the ones that have, the most use in terms of like the energy consumption or the energy value. So our monosaccharides, we've got this right here. This takes us back CH2O. Whenever you think back to Gen Chem 1, there's a term where you learn about a, sorry, just a second. Um, you learn about a molecular formula and then another type of formula. It starts with an E. Add it to the chat if you know which one I'm talking about. Empirical. Perfect. The empirical formula. So your monosaccharides have the empirical formula of CH2O. Now, whenever we see that, so everything kind of has that ratio, 1 to 1. Or sorry, that's 1:2:1. Um, the configuration that biochemists like to use is they like to throw that X down there and then put H2O in parentheses and say X outside of that. So if we have something like, a 6 carbon sugar, well, that 6 plugs in there. And then just like in Gen Chem 1, that 6 also plugs in here and applies to anything within that parentheses. So one example of a monosaccharide would be glucose. Another would be fructose, ribose, galactose, and then glyceraldehyde. These are all some common examples of monosaccharides. I've got a slide where I show you the ones that I want you to be familiar with. But I think that glucose is a great place to start. Fructose is a great place to continue from there. Now, with that in mind, we can take the number of carbons and use that to come up with a nice term to sort of support that. So we use our prefixes, 3, 4, 5, 6, 7, 8 carbons to indicate, well, the size of a sugar. Now, does anyone know, well, actually, look at this slide and go ahead and tell me and share with me what you think the suffix that is typically used for most sugars. We've got hide. Oh, OSE is what I was looking for. OS. So glucose, fructose, ribose, galactose. So that OSE suffix is usually indicative of a sugar. Now, with that in mind, we can use these prefixes to come up with another term to describe both glucose and fructose. These both are carbons with 6 or sorry, these are both sugars with 6 carbons. These are both examples of hexose or ahexose. These are both hexoses. Now, if a sugar has 5 carbons, it's a pentose. Now, that key word or that key, yeah, letter slash word is ahexose. What that means is that there are lots of hexoses. And you could say that glucose and fructose are isomers of one another. Now, there's lots of classifications when it comes to sugars and giving them different names and terms. Just as we can describe a sugar based on the number of carbons it has, we can also look at any functional group that it may have. For example, the two sugar functional groups, aside from alcohols, that are important for you to know about are aldehydes and ketones, the presence of an aldehyde or a ketone. If you have a sugar that has a aldehyde functional group, one person just told me they can't see slides. Can anyone else see slides? Can I get a confirmation that, okay, I'm getting one. I'm going to go ahead and stop my share and have this pop up again. See how that goes. I hope that resolves it. Otherwise, I would recommend that you log out and log back in again. Um, or I'm guessing if my, okay, so, okay. That is too bizarre. This happened in one of my classes earlier today. I don't know why that is. Hmm. Maybe it has to do with like whenever I started the share and okay. It said the meeting was in focus mode when I logged in, but it's a great question. I wouldn't think so. Um, at any rate, if that happens again, anyone, and you don't see slides, but you see me just talking and talking and talking, um, just let me know. So thank you for letting me know. Okay, so if we take something like glucose, now rats, I need to go back to my using my pen. Um, Glucose is an example of a hexose. Glucose is a sugar with an aldehyde functional group, so it is also an aldose. Another term that you could use to describe glucose is you could say that it is a hexose. You could also say it is an aldose. You could also put those words in a blender and come up with aldohexose. In which case, well, you're combining those two things. Now, glucose is the common name, and most sugars that we talk about in this class, we're going to be referencing the common names of them. So, aldoses, ketoses, aldohexose, all kind of describe a variety of different molecules. This right here, let me make sure. Okay. This right here is a 3-carbon sugar. So what would you call this? Or add to the chat a term that you would use or terms that you might use to describe this specific molecule without identifying what it is. Okay, yeah, it does have a chiral center. But I was kind of leaning more towards the terminology that we just talked about. It has an aldehyde, triose. Yeah, it's a triose. And by virtue of it having an aldehyde, we could call it an aldotriose. Okay, so one of your classmates brought up that this is a chiral molecule, and I'm happy that you brought that up because we'll talk about a couple of different chiral centers in this molecule and other molecules. But if you look at carbon and if we look at the carbons of this molecule, this is going to be carbon number 1. This is 2 and 3. Now, this specific molecule is known as glyceraldehyde. This is basically the simplest sugars that you can come up with that has an aldehyde. You could also have a 3-carbon molecule with a ketone. But this right here is our aldose, our aldotriose. Now, from there, we could look at this right here. Does this have an aldehyde functional group? Our aldehyde functional group right up here. Yeah, it's got that same sort of thing. It's wearing the same hat. So we're looking at an aldose. And if we wanted to use that same sort of logic, we've got carbon one, two, three, four. So an aldo tetros. Does everyone follow that so far? Does anyone want to guess where we're going next? That's right. An aldopentos. There's our aldopentos. Carbon number one, two, three, four, and five. Now, one of your classmates alluded to, well, our first molecule, our glyceraldehyde, being a chiral molecule. It is. Now, when we look at this and we think about chirality, so whenever I think of chirality, my kind of working definition is I'm looking for a atom that has four unique groups bound to it. So if I look at the molecule that I've got highlighted with that I have labeled, carbon number one, does that meet the criteria of having four different groups bound to it? Nope. So that is not a chiral center. What about carbon number two? Well, it's got a hydroxide. So I'm going to put a check mark there. It's got a hydrogen, and then it's got this aldehyde, and then it's got this little chain right here. So carbon number two, yes, it is chiral. Okay, so I'm going to keep track of chiral centers. Now I've got carbon number three. Well, I've got a chain, two carbons, and then a chain that's two carbons, but one of them's an aldehyde at the end of it. So we've got carbon two and three that are chiral centers. And then, last but not least, I'm going to undo those. Carbon number four, actually not last, I'm sorry. Carbon number four, got this chain, and then that right there. So carbon number four is a chiral center. Now, if you're thinking to yourself, oh, sheesh, I took organic. Thought I was free from there. You are, don't worry. This is close to the extent of my enjoyment of organic chemistry. Um, so don't fret. Um, Now, with that in mind, carbon number five, is that a chiral center? Yes or no? Throw it in chat. No, it is not a chiral center. I got a question about if we are headed toward Fisher projections. Yes, we are. And I've got the PowerPoint up, so if you ever want to like flip ahead, you're more than welcome to do that. So yes, we are headed toward Fisher projections. So our next sugar, we've got a five carbon sugar. Lo and behold, this one right here. This linear molecule, this specific one, is glucose. When it comes to learning the structure of glucose, what I would recommend that you do, one, two, three, four, five, six. Okay, we've got six carbons. Carbon number one and six. Well, this is okay. I'm providing you with the way that I learn the structure of glucose. And glucose is important because, well, your cells need it, and it's so central to any metabolic process. Um, Carbon number one, well, you know that that is going to be your aldehyde functional group. Carbon number six is not a chiral center. So whenever I draw glucose, I draw it like this. 4, 5, 6. CH2OH. Okay. And I'm saying all this because Whenever I show you more structures of sugars, it's intimidating, and you might say, like, oh my gosh, do I have to learn all of those? And the answer is no, not really. Um, but what's helpful for me is whenever it comes to learning the structure of glucose in its linear form, I look at my hydroxide groups. And the hydroxide groups follow a pattern for me, and that is right, left, right. Now, I didn't include carbon number five. We're going to get to that in just a little while. But anytime someone says glucose to me, I think right, left, right, because that gives me the information that I need to basically draw my structure of glucose, which again, carbon five we'll get to in just a moment. Okay, so with that in mind, this is kind of our progression for our different monosaccharides. Um, if I were to scramble this configuration around and let's say put my hydroxide group that was on carbon number three, rather than being on the left, if I put it on the right-hand side, I'm going to throw my hydrogens here. Is this glucose? No, it's not. Why is it not? Well, glucose has on carbon number three a hydroxide group on the left-hand side of my structure. Whereas this molecule that I just drew, where is the where is the hydroxide group on carbon number three? On the right. So the position question, go ahead and add to the chat if you have any questions. And yeah, or if you want, you're more than welcome to unmute yourself. So this is glucose, not. It is absolutely still a hexose. What also is it? They can, but whenever we have that rotation, we're changing the sugar altogether. It's also an aldose. So this is an aldohexose. And the reason for that is because typically glucose is going to find itself not necessarily in this linear format, but rather it's going to be in a cyclic rate, or it's going to be in a cyclic form. Okay, so now we're going to go on to distinguish between aldoses, ketoses, D sugars, and L sugars, and a pair of sugars as epimers. So what I hope that you got from what we just went over, the progression from looking at an aldose, a ketose, a hexose, a pentose, a heptose, an octose, prefixes, numbers of carbons, and everything like that. Now, whenever we're talking about an aldose versus a ketose, well, we have an aldehyde functional group indicative of an aldose, or we have a ketone functional group indicative of a ketose. Okay. Then from there, like that's the biggest difference. Now, oh, they do. Okay. So from there, what we've got is here's a pair of sugars. If we look at the sugar that's on the left-hand side and the sugar that's on the right-hand side, we've got a mirrored plane that basically reflects these two sugars from one another. So these two sugars are mirror images of one another. Now, the terminology that biochemists use to describe this, whenever we have sugars like this, is a couple of different things. Whenever you see, and okay, so is everyone in agreement that this is an aldotriose? Okay. Now, when you look at this molecule, what is the number of our highest numbered chiral carbon? Carbon number two is our highest numbered chiral carbon. Okay. Now, when you look at carbon number two, The molecule that's on the left-hand side, where would you describe the hydroxide group as being on the left or the right-hand side of my molecule or of the molecule? Okay, left, great. Now, the other one, well, I think it's safe to say that that hydroxide group is on the right-hand side. Whenever you look at a sugar, what you always want to find is the number of the highest numbered chiral carbon. That's one way to define this. Another way is some people refer to this as the penultimate carbon, the second highest numbered carbon. Now, this is significant because that is going to ultimately influence what type of molecule this is from the stereochemistry perspective. Is this a D sugar or an L sugar? If your hydroxide group is on the left-hand side of your molecule, this is an L sugar. If your hydroxide group is on the right-hand side, that is a D sugar. Now I'm referencing one specific carbon. Which carbon is it? The highest numbered chiral carbon. Now, does that mean that you can look at a hexose or a pentose and say, aha, I need to look at carbon number 2? No. Carbon number 2 is specifically significant for a triose. Now, with that in mind, if we look at these molecules, my question for you is, are either of these glucose? And I know that I just showed you the structure of glucose, but I'm kind of leading and using the tone of voice to say that yes. Okay. Now, okay, we got a contribution that they both are. I got a vote of left is glucose. They're both glucose. They are both glucose. Okay. Now, this molecule that's on the left is what I'm going to look at is Madison's absolutely right. There's L and D. Okay. Now, I'm going to start with this molecule on the left-hand side. What is my highest numbered chiral carbon? Carbon number 5 is my highest numbered chiral carbon. And I look at my hydroxide group. It's on the right-hand side. That's my indicator that this is a D sugar. So this is D something. Now, like I said a little bit ago, the pattern that I look for whenever I'm looking at a molecule to see that it is glucose is I look at right, left, right. Carbon number 2, 3, and 4. Is it glucose and dextrose? I think that dextrose is just another term for glucose. Um, I'm happy that you brought this up though, because, and I'm gonna, okay, so I've got right, left, right. Then if I look over here, my other molecule, what do I have? I've got my highest numbered chiral carbon, carbon number 5, and I've got my hydroxide group on the left-hand side. Well, that is an L sugar. Now, in this case, what I'm looking at is rather than right, left, right, I'm looking for left, right, left. Because the D sugar of something is the mirror image of the L sugar. Okay? Now, with that in mind, does anyone know off the top of their head? I got a private message. Is 5 the highest solely because it is connected to um No, it's the highest because if you count up, we identify all of our chiral carbons, this one, this one, this one, and this one. These are all chiral carbons, and five, and then sorry, this carbon right here is not a chiral carbon. So it doesn't really, the reason that we pick five is because that's the highest numbered chiral carbon. Okay, so this molecule right here, L-glucose, is basically biologically irrelevant. And what I mean by that is every enzyme in your body that is responsible for metabolizing sugars is going to be stereospecific and it's sensitive to any stereo variation. So it will see this D isomer and be like, perfect, I'm going to metabolize that. It's going to see the L isomer and say, not interested. Now, with that in mind, I always like to kind of bring this up. So is it the highest numbered chiral carbon? Yes, it is the highest numbered chiral carbon that determines L versus D stereochemistry. Right hand side is, well, that's where you're ending up with the D configuration. So a question that I got earlier was, is it glucose and dextrose? And, I don't really know exactly which kind of population of folks use dextrose. I think it might be, I don't know if that's like a clinical term. I don't know exactly, but D in this case stands for dextrorotary, just as L stands for levorotary. I said that I wasn't going to bring up organic chemistry a lot, but there I go again. Um, Dextrose is D-glucose. I looked it up. Sorry. No need to apologize. Um, so with that in mind, this L-glucose, I always like to mention this that it's kind of biologically irrelevant, but it's still significant. It is if you were to, let's say, drink a Coca-Cola that had L-glucose as opposed to D-glucose, your, you know, my understanding is that it would be just as sweet, but your all of the cells that are responsible for glycolysis and breaking down sugars isn't going to really do anything with that. In which case, it's kind of an artificial sweetener. Now, with that said, the price point on like 1 gram of L-glucose versus D-glucose is considerably different. So, that's where I like to bring up if I won the lottery, there'd be signs. I would drink Coca-Cola's flavored with nothing but L-glucose. Only the finest L-glucose will I drink. That and I would never re-wear a pair of socks. Wasteful, but luxury. Okay, so this is glucose. We've got D-glucose and L-glucose. Would it raise your blood glucose levels? I presume. I mean, my inclination would be to say no, but just because of the fact that the way that the sugar is going to enter any of your cells is with transporters that are going to be just as sensitive as the enzymes that are responsible for metabolizing it. So I would bet that L-glucose would probably just go straight through you. But I don't know. That would be my guess. But then again, that's also where I'm like, whatever that was shared with me as a graduate student, I was like, oh, but how would it still be sweet? And I don't know. At any rate, we'll proceed. So when we talk about D-glucose and L-glucose, I saw somebody mention this earlier. These two sugars are enantiomers of one another. It's very tempting to look at, oh, well, this is D-glucose and this is L-glucose. And one of the things that people like to say is they like to say, oh, well, if you just switch the positioning of the hydroxide group on the the highest numbered chiral carbon, then you've made the new sugar. But if you look at these two, is the difference between L-glucose and D-glucose the positioning of the hydroxide group on one single carbon? No, it's not. It's actually the positioning of hydroxide groups on four different carbons. All of our chiral carbons, they all get flipped because they're mirror images of one another. So D sugars and L sugars, as long as you're talking about D glucose and L glucose, D galactose and L galactose, they are mirror images of one another. They are not just switching one hydroxide group. So be careful and be wary of that. Now we can proceed. Okay, here what we have are a couple of sugars that are not mirror images of one another. If you look at these two sugars, I think that whenever it comes to sugars, it's helpful to say, all right, well, break down your process. Okay, I'm talking about sugars. Now I'm talking about aldoses. Now I'm talking about aldohexoses. These are two aldohexoses. Which carbons are basically configured the same way? Two, two, same. Three, three, nope. Four, four, nope. So we got variation of two different groups. Notice I did not go to carbon number 5. Why is that? Well, one, I kind of saw it with my eyes, but also these are both D sugars. If I were to switch this around, well, then I'd be comparing a D sugar to an L sugar, in which case it gets a little bit more complicated. Now, whenever we have variations at 2 or more carbons, these are known as diastereomers. Now, if you're thinking, man, this is getting kind of complicated, then you understand the plight of a young Avril Lavigne. Avril Lavigne wrote the song Complicated about sugar chemistry. So, diastereomers, we've got enantiomers, we've got diastereomers, and last but not least, we've got epimers. What is the difference when we look at these two sugars? One, they're both D sugars, so we're good there. 2, same. 3, same. 4, different. Okay, so a diastereomer has variations of hydroxide group positioning at 2 or more carbons. Epimers, by contrast, only have variation of about 1 carbon. When you compare two different sugars and you say, oh, well, the difference is only one specific hydroxide group. Well, then those are an example of a pair of epimers. Now, I've got a poll question. Booyah! It's up. Are L and D glucose epimers of one another? Going in the right direction, which just makes me think of the band Robert Randolph and the Family Band. If you've never heard of them, look them up. Look them up. Also, if you've never heard of them, yeah, not a lot of people have. I'm not saying that as like a flex. I'm just saying like they never really got the critical acclaim and appeal they deserved. Okay, so I'm gonna go ahead and stop the poll. And 70% of the class said, no, it seems like they are though. And 70% said, yes. 30% said yes. I'm sorry. Well, 30% of you, I'm sorry, but are incorrect. If you remember, stop my share, jump back. These are enantiomers. L-glucose and D-glucose are enantiomers. Because what is the difference? Basically, how many carbons have hydroxide groups in different positions when we look at D-glucose and L-glucose. If you wanted to put it bluntly, we've got four hydroxide groups that are in different positions, and different positions being on the right or the left side. Carbon number 2 in D-glucose. Well, D-glucose, it's on the right-hand side. L-glucose, it's on the left-hand side. Every single hydroxide group is flipped from a D sugar to an L sugar. Now, an epimer, that is where only one hydroxide group has been positioned differently. So this sugar that we've got here on the left, this is D-glucose. This sugar on the right-hand side. My first question is, and we can kind of go through the process, is this an aldose? Does it have an aldehyde functional group? It does. Okay. Then I want to count up my carbons. 1, 2, 3, 4, 5, 6. Is it a hexose? Yep. So then we could say, is it an aldohexose? Yes. It is an aldohexose. The next thing that we can say is is it an L or a D aldohexose? Well, we're going to go straight down to carbon number 5 because as a hexose, 6 carbons, our second highest numbered or our highest numbered chiral carbon is number 5, in which case this is a D aldohexose. The pattern that I personally always remember, just kind of as like a muscle memory thing for glucose, is right, left, right. For this, I've got right, left, left. So carbon number 4. This specific sugar is known as the C4 epimer of D-glucose. Now, I remember the first time that I taught this, somebody said, is that where we get C4 from in terms of the like explosive? No, it's not. Okay, moving on. Next learning objective. Describe the relationship between glucose and galactose. Glucose on the left, galactose on the right. Is that where the C4 energy drink name comes from? No, I think that comes from, it has crack, cocaine, it's crimson colored, and then there's cottage cheese in it. Not really, I made that up. Oh, Abdullah, you had a fantastic question. Would a glyceraldehyde have an epimer or an enantiomer? It's fair to say that the enantiomer of glyceraldehyde is also the epimer of glyceraldehyde. D and L, they're enantiomers and they're glyceraldehyde. And they're epimers of one another. Okay, now when looking at glucose and galactose, would anyone care to add a sentence describing the relationship between glucose and galactose? And I'm sorry, I shouldn't have said that about C4 energy drink. I don't know what it is. They're two different molecules. True, I agree with that. But let's try to use that terminology, epimer. They are epimers. If you wanted to be as descriptive as possible, galactose is an epimer of glucose, yeah. Could you say which epimer? You could say that, well, galactose is the C4 epimer of glucose. You could also say that glucose is the C4 epimer of galactose. Carbon number 4, right here, and right here is where we have the variation. This is a way that you can describe a relationship between two different sugars. Now, with that said, I want you to know the structure of glucose and galactose. If I were to draw something like this, Okay. This molecule that I just put together, my question is this molecule that I drew in red, is it an epimer of glucose? Yes or no? Yes, it is. It is an epimer. It is the C3 epimer of glucose. Fantastic. Now, let's push this one more step. Is this molecule that I drew here all in red, is it an epimer of galactose? You're right. It is not an epimer of galactose. Because, well, how many carbons have a difference, or how many hydroxide groups are positioned differently? It's a diastereomer. Yeah, carbons 2 and 3. Well, no, 3 and 4. These guys right here, or those two right there, are different between the molecule in red and and I'm happy that you said 2 and 3. Don't forget, carbon number 1 is our carbonyl carbon up there. Okay, so that's just sort of get comfortable looking at it that way. Okay, so an epimer is uniquely a variation of about one carbon. If it's more than one carbon, they're diastereomers. Okay, um, now we'll proceed. Like I said, I'd show you all the aldoses. I'll show you the world. Aldoses, ketoses, so many different options. Now, with that in mind, these sugars that you will see more times than not are going to be the ones that are in boxes here. What I want you to know about is I want you to know the ones that are in boxes. Now, if you're thinking, okay, I need to prioritize some of these structures. First thing that I would do is prioritize knowing the structure of glucose and then find out the relationship between glucose and mannose. Does anyone have that right now? Can anyone put that together? Glucose and mannose. Mannose is to the right of it. Mannose is the C2 epimer of glucose. You're absolutely right, Abdullah. Great job. Galactose is the C4 epimer. So essentially, if I've got 5 structures that I want you to know, well, if you know the structure of glucose, and then you can remember mannose is a C2 and galactose is a C4, you're in good shape. Ribose is an aldopentose, and glyceraldehyde is an aldotriose. Those are the 5 structures that I want you to know about. And those will be ones where I just say, what is this structure? Okay. Here we've got our ketoses. We haven't talked about them so much. The only structure that I want you to know of your ketoses is fructose. Sometimes fructose is known as the the ketose version of glucose. Now, a fair question for that is why? Well, if you think about the structure of glucose as, I'm going to say gluc is, here's carbon 2, 3, 4, then 5 with a hydroxide group showing that it is a D sugar. Well, D fructose, we've got hydroxide group on the right-hand side. Carbon number 4 has a hydroxide group on the right-hand side. 3, hydroxide group on the left-hand side. And then carbon number 2, well, that's where our functional group is. So fructose equals ketose version of glucose. So it's almost like, yeah, here we go. I'm putting it together in my head. Fructose is glucose, but then no, I was going to make some dumb joke about, oh, it's the Taylor Swift version, but I can't put it together in my head, so it's not working. And it's best that I stay away from like pop culture because I don't really not good at it anymore. Okay, so here we go. Now recognize the structure of ribose, glucose, fructose, and the Hayworth and Fisher projections. Okay, so the structures that we've been looking at are known as your Fisher projections. The Hayworth projections are the ones that you're going to see more times than not. This is an example of a Hayworth projection. And spoiler alert, this is the example of D-glucose as a Hayworth projection. Now, this is our Fisher projection on the right-hand side. That's the one that we've looked at previously. So sugars like to cyclize. Typically in your body or any one of your cells in your body, well, it's actually it's the chair or the boat configuration that exists, but this Hayworth projection shown on the left-hand side, I'm going to draw an arrow to it, is the one that biochemists use typically. This bolded line or this bolded line is kind of coming forward. And so one of the pieces of terminology that I think is worthwhile is to imagine that this hexagon that makes up that ring is kind of a flat surface. Just imagine that as a flat surface. And therefore, things, meaning functional groups, are either pointing up or pointing down from that functional group. Now, an example or from that ring, this hydroxide, this, and this, these are all pointing down from the ring. This and this are pointing up. So groups are either pointing up or down with respect to our functional or with respect to our ring. Now, with that in mind, the biggest and the trickiest part about this is translating a linear molecule to the cyclic form. This is carbon number 1 right here. 2, 3, 4, 5, and 6. I always like to ask this because everyone, typically figures this one out pretty easily. Can you look at the Fisher projection and then look at the Hayworth projection and identify carbon number 6? Yeah, it's pretty easy. That guy is that guy. Okay. Now, what I like to do is I like to count down. So this is carbon number 6. Therefore, this is 5. Now, what we're going to do is we're going counterclockwise. So 4, 3, 2, 1. What you might look at is think, oh, is that like totally arbitrary? No, it's not. This oxygen right here that I'm putting a box around, and we'll cyclize this in just a moment, is this oxygen right here. What that means is that carbon number 1 here, well, if you look at that, this is a single bond. I don't think anyone's going to argue that. This carbon right here has a single bond. There's 1. There's 2. Here's 3. And then what do organic chemists love to omit? Carbon-hydrogen bonds. So they love to omit those hydrogens. So with that in mind, this carbon right here, carbon number 1, wow, it picked up that hydrogen. What does that mean for carbon number 1 in its chirality? Has it changed as it went from the linear to the cyclic form? It has. It is now a chiral carbon. So this carbon number 1 right here is chiral. Now, we're going to come back to that in just a moment, but for the time being, what I want you guys to look at is I want you to look at carbon number 2, 3, and 4. In the linear form of our molecule, we use the pattern right, left, right. Could anyone come up with kind of a pattern to translate right, left, right to the cyclic form? Down, up, down. Carbon number 2, down. Carbon number 3 is up. Carbon number 4 is down. Okay, so right, left, right means down, up, down. So then my question for you guys before, and just kind of imagining this, If I said, oh, I wanted to draw the Hayworth projection of the C4 epimer of glucose. This is glucose. What would my pattern be? Rather than right, left, right, it would be down, up, then what? Down, up, up. Okay. So translating a linear form, right side means down, left side means up, as long as you're talking about a D sugar. Now, with that in mind, I always like to teach this class thinking about, well, we're narrowing our scope to something more biologically relevant. What did I say about L sugars and their biological relevance? Yeah, not particularly relevant at this point in time in human existence. Does that mean that they are completely irrelevant, that they have no clinical significance? No. What I'm getting at is they don't really have any sort of biological relevance that's known to date. With that in mind, whenever it comes to, oh, I'm drawing a sugar, you could go through 100 different questions of MCAT prep, PCAT prep, any sort of test prep or anything like that. And you're basically, it's going to be rare that you find a L sugar and draw the L version of this sugar. So I'm operating under the idea that when we're talking about a Hayworth projection, we are talking about the D variation of that. If I wanted to draw the L variation of that, what would I do? I would basically invert every single carbon, in which case I'd draw a mirror about a different plane. So what I'm doing is we're narrowing our scope and we're talking about D sugars. When we talk about linear sugars, we'll talk about D sugars and L sugars, but when we're talking about our Hayworth projections, we're going towards our D sugars pretty exclusively. Now, going on from there, I want you guys to be able to know the reactions to form cyclic sugars and the sugar forms that are predominant in solution. So here what we have are the functional groups. So up on the right-hand side, we've got our linear form of glucose. I'm sticking with glucose because of its importance. When we look at glucose, we know that it's an aldose. Boom, aldehyde. And then over here, we've got an aldehyde. What do aldehydes like to do? They like to react with alcohols because that carbon of that aldehyde, partial positive. What about an alcohol? Partial negative. Now, when you look at that, you might see this and be like, ooh, but oh man, I'm seeing, what is that? Five different alcohol or five different hydroxide groups, five different alcohols effectively. Yeah. Whenever those two things react, an aldehyde and alcohol, we form a hemiacetal. Okay. Why did I draw a six-membered ring there? What do we know about ring stability and ring size? Typically, five and six-membered rings are your most favorable. Can you form a seven-membered ring? Yeah, absolutely. Can you form a four-membered ring? Yep. Three-membered ring? Yep. Two-membered ring? I don't think that's possible. That's just a line. So here what we have is we have an aldehyde. This is our aldehyde. This is our aldehyde. So R1, this is this. Our alcohol, R2. Here's the alcohol. Here's the alcohol. And where is my R2? Well, it's this right here. So we have some overlap. So this is cyclizing. Now, this oxygen right here is this oxygen right here that is within our ring. So what we see is that right there. Booyah. That's the cyclization of glucose. Right, left, right translates to down, up, down. Carbon number one becomes a new chiral center whenever we form this new ring. Notice how I've got a model right here on the lower right-hand corner that has my hydroxide group pointing down on carbon number one. And then as my sugar cyclizes, where does my hydroxide group on carbon number one go? Goes up. You're absolutely right. Does that mean that it's not glucose? It's not what it means. But instead, what that means is we could have a different variation of sugar, of glucose. I'm going to get to that in just a moment. But in the meantime, we have kind of the same operation going on with a ketone, which is capable of interacting with, or reacting with an alcohol to form a hemiketal. So a hemiketal is another version of a cyclic sugar. So the difference between our sugars here is this is a five-membered ring. A five-membered ring is a furanose, whereas a six-membered ring, this is glucopyranose. A five-membered ring makes a furan, and a six-membered ring makes a pyran. Okay, so, oh, sorry about that. Now, does anyone have any questions about this so far? We've been over a lot of stuff. And actually, I'll jump back just a tad. Um, Whenever we have, no, I'm good. Okay. Okay. So from there, where I want to go, I'm not sure. Okay, fair enough. I
I
want
have
you
a
to,
question.
yeah, go for it.
Can you just repeat with the R1 and R2 groups on the cyclize? Yeah, on that slide, how you pointed out. Yes, the overlapping.
Sure. So essentially, what we've got here with our two different models, an aldehyde reacting with an alcohol, um, this is kind of implying R1 and R2. This is implying that these are um, from separate molecules and that those R groups are just different from one another. But here, the alcohol and the aldehyde, that carbonyl carbon, they're on the same molecule. So if we were to look at the aldehyde, our R1 is this whole chain right here. And then I'll switch colors and I'll go to, let's go with blue. My R2 is anything that's attached to my hydroxide. So it's going to include all of this right here. So I don't want you to worry too much about that, but just instead think about that as, well, R2 is, that's why we have our oxygen here is a member of our ring, as opposed to it being, well, not a member of the ring. And that's how this aldehyde here now has a hydroxide group, which is indicated right here. Does that help?
Yes, that makes more sense. Thank
Okay.
you.
Okay. Great. Thanks for asking. Okay. So with that, given the starting sugar, be able to identify the corresponding methylated or N-acetylated carbohydrate. Then be able to recognize and draw the common sugar derivatives, aldonic acids, uronic acids, sugar alcohols of glucose. Again, this is keeping it all kind of glucose centric because, well, glucose is the center of the sugar energy extraction world. So, what we've got whenever we have a cyclic form of a sugar. So, this right here is our, let's see, down, up, down on carbons two, three, and four. This is glucose. Our new chiral center, carbon number one, is what's known as an anomeric carbon. This is a new chiral center. Okay. Now, what is important to notice and recognize whenever you look at the structure of a sugar is to think about this functional group, this hemiacetal. Our basically our oxygen here is this right here. This carbon is this carbon. This hydroxide is this hydroxide. So our R1 and R2 is basically the backbone or the carbons that make up the backbone of this ring. Now, a anomeric carbon, this is, sorry, what is important and significant about this is that, oh, sorry, um, sugars and ringed forms, what they happen to do is they open up and then they close. So it's kind of like a clam. They open and they close periodically. And whenever they open and close, what happens is that this hydroxide group will rotate up or rotate down. And this is a phenomenon known as rotation. And what that leads to is this interconversion between the alpha and beta forms of a sugar. So if we were to look up, or if we were to look at these, this right here, and now this is very frustrating. I'm about 98% sure that this is oh, dang it. That's not what I want. Um, when my hydroxide group on my new chiral center is pointing down, this is my alpha variation of glucose. So alpha, the hydroxide group on our new chiral center is pointing down. Alternatively, the beta configuration is where this hydroxide group is pointing up. So we have an alpha and beta form of the cyclic variation of glucose. Now, what we have happen with our hemiacetal and with this anomeric carbon is these love to react with an alcohol. And when they react with an alcohol, these two hydroxide groups right here, what they're going to do is they're going to basically serve as a branch between, in this case, my ring and this ethyl group right here. So this is ethanol reacting with glucose. A hemiacetal reacting with an alcohol, which is going to produce an acetal. Now, what does that acetal look like? Well, that acetal looks like this right here. And the significance of this is that we form a glycosidic bond, also known as a glycosidic linkage. So I've presented quite a bit of new terminology here. There's alpha and beta anomeric carbons, or anomers. Alpha, the C1 OH is pointing down. And beta, C1 OH, points up from my structure. When an anomeric carbon reacts with an alcohol, so a hemiacetal, which is where my anomeric carbon is, reacts with an alcohol, we form an acetal and some water. Now, the significance is not I don't want you to be thinking like, okay, so I need to be concerned with the reaction of ethanol and glucose. No. The significance of this is how disaccharides form. So polymers of multiple sugars, of two sugars put together, that would be an example of a disaccharide. Okay, so these are a part of a class known as glycosides. So a glycosidic linkage or a glycosidic bond is a hallmark of a glycoside. Now, Derivatives of sugars. Well, here's one example of a derivative of a sugar, which is N-acetylglucosamine. Okay. Now, before you get intimidated by this, if where I scribbled a bunch of blue there was a hydroxide group, what would that molecule be? Add it to the chat. Glucose. That's all that it is. It would be glucose. Now, I didn't. Instead, I scribbled over blue or scribbled over a molecule, this functional group right here. This is, let's see, one, two carbons. How many carbons does acetic acid have? CH3COOH. An acetyl group. N-acetylglucosamine. So that's where that's coming from. These derivatives, they tend to be a little bit more intimidating just structurally. You're like, oh my gosh, I've never seen this before. We'll cover up the part that looks like you've never seen it before and then be like, oh yeah, that's glucose. And then let's try to put together a name from that. Do I know of a two carbon molecule where there's a carbonyl carbon and a methyl group? Yeah, I've got something close, acetic acid. That's something that I'm somewhat familiar with. Now, so your N-acetylglucosamine is one example of a derivative. Another example of a derivative is glucouronic acid. Glucouronic acid. Now, again, let's think about this molecule. Do we have our aldehyde functional group? Yep, that's intact. Carbon 2, 3, 4, 5. Then we've got carbon number 6. What's that? Is that an, yeah, looks like a carboxylic acid. So we added a carboxylic acid onto carbon number 6. That's glucouronic acid. Anytime you see uronic acid, basically what's been done is that sugar, carbon number 6, which was historically CH2OH, a bland and boring variation of a use of a carbon, we replaced that with a carboxylic acid. That's where that uronic acid comes from. Next up, well, glucose can be reduced to make a sugar alcohol known as sorbitol. What's the difference between glucose and sorbitol? Well, carbons 2 through 6 are the exact same. So then carbon number 1, rather than it being, well, an aldehyde functional group, we've instead made it look exactly like carbon number 6, CH2OH. We've reduced this. We've reduced glucose to sorbitol. Okay. Now, the last thing for the day is determine if a sugar is a reducing sugar. Here are a combination of different sugars. Whenever you're asked to look for and determine if a sugar is a reducing sugar, what you always want to look for is the anomeric carbon. And a fair question there is, how the heck do I identify an anomeric carbon? Because don't I need to know the structure of the linear form of this? What you're looking for when you want to find an anomeric carbon is the following. Okay, there is my ring. There's my 5-membered ring. And I'll go ahead and draw it. No, I don't need that. I'm going to stop right there. What I look for anytime I'm trying to find my anomeric carbon, the carbon that determines if I'm looking at an alpha or the beta configuration of a sugar, is I look for where is the oxygen within my ring. Then what I look for is, okay, where is the adjacent carbon to that? Okay, well, here's an adjacent carbon. and here's an adjacent carbon. Then, which one of these adjacent carbons has a hydroxyl group? And I'll, just for the sake of, I am looking for my oxygen within the ring and then a carbon with a OH group on it. I've got this one or this one. I'm going to label it B or A. Well, A, that's a carbon adjacent to my oxygen within my ring, and it has a hydroxide group. B, well, that's a carbon adjacent to the oxygen within my ring. Does it have a OH group? It does not. So once I find my anomeric carbon, I want to see, does that anomeric carbon still have that OH group, or is it something like this, OCH3? If that OH is still intact, then that is the reducing end of my sugar. If that OH has been replaced by an OCH3, well, this is a glycosidic linkage, just to bring the terminology back. And this kind of end of my sugar, I can do better than that. This is now a non-reducing sugar. In part because, we go back just a moment. Yeah, no, this is fine. We're looking for a hemiacetal. We're not looking for an acetal. So now if I go back to here, this whole thing, well, that's an acetal. It's no longer a hemiacetal because that hemiacetal reacted with CH3OH. So that reaction is done. It's taken place. So this is a non-reducing end, and it is a non-reducing sugar. So sugars are classified as being either reducing or non-reducing. Look for a anomeric carbon and see if it's free. This right here, if we look at ribose, we've got our anomeric carbon and a hydroxide group attached to it. Lactose, we've got, here's an anomeric carbon that is bound to another sugar. Here's an anomeric carbon and it's bound to an OH group. So this is free, this is bound, so this is a reducing end. Now, the opposite end of the sugar is also going to be a non-reducing end. So there are some sugars that are reducing sugars and some sugars that are non-reducing sugars. Okay, does anyone have any questions about that? Absolutely. So you're getting there. So if we look at, I'll go back here. Here is glucose. Anyway, I'm just going to be fielding questions. I'm going to record this. I'm going to post this on the Canvas page. So if you got to go, then I hope you have a wonderful evening. If you're going to hang around, okay, cool. So we've got our sugar here on the right, and then I'm going to draw another variation of this same sugar. Got down, up, down. And carbon number 1, that is my new chiral center. The difference between these two sugars, well, there's only one difference, and that is the hydroxide group on carbon number 1. This one that I've just drawn an arrow to, I'm going to refer to that as being up. And the other hydroxide group, which I'm changing the ink of my pen, that I'm now circling, this is down. Now, whenever you cyclize a sugar, that hydroxide group may end up pointing upward. It may end up pointing downward. The difference between these two sugars, my first question for you is, are they both glucose? They are. They are both glucose. This one on the right, this is known as alpha glucose. And the one on the left is beta glucose. Does it have to be cis or trans to carbon 6? That's a great question. So typically, whenever we draw, um, okay, so typically, whenever we draw carbon number 6, and anytime we're drawing a cyclic sugar, it's going to be in the upward facing position. So the absolute best definition for defining if something is alpha or beta is alpha is going to be in the opposite direction of carbon number 6. Beta is going to be in the same. Now, I say that, and you can operate under the idea as up is beta and down is alpha, just because 99 times out of 100, carbon number 6 is going to be pointing upwards. But that's a great question. That's a fantastic question. Are there any other questions? Okay. Would you like to ask it privately? Or if I'm going to go ahead and say, everyone, you can take off. Have a great day. And then I'm going to ask you to join a breakout room. But everyone have a great day, and I'll see you guys on Wednesday.